The purpose of RE is to stabilize the operating point. RE is going to provide a negative feedback. So the voltage across RE that will be used as a negative feedback voltage. So whenever there is a increase in the collector current with the temperature, so when the operating point shifts moves up in the DC load line, when IC is increasing, so the operating point moves slightly above than the fixed value, then which is fixed in the middle of, actually in general the operating point is fixed in the middle of the DC load line for faithful amplification. But with the temperature dependency of the transistor, the collector current increases because the reverse saturation current doubles for every 10 degrees centigrade rise in temperature. So the collector current increases with temperature. So when this shifts the operating point up in the on the DC load line in the upward direction towards the saturation, so this increase in the collector current is to be we have to bring back the collector by decreasing the same value. So whenever there is increase in the collector current, so the emitter current also increases accordingly, because so IE is equal to IC plus IB. Since IB is constant, so whenever there is an increase in the collector current, there is a corresponding increase in the emitter current. That emitter current, when flows through the RE, produces voltage. So that voltage will act as a feedback voltage, negative feedback voltage, that will be connected as input, connected back to the input as a feedback voltage. So therefore this will going to reduce the VBE because VB is constant. Since IB, we are fixing IB constant, and therefore VB is also constant. VB, so the VBB, so therefore VBB is constant. VB, that is the voltage at the base point, is going to be constant. VB is constant. Since we have the equation VB, which is constant, VB is equal to VBE plus VE, and VB, this is going to be a constant because IB is constant, so VB is constant, VB is constant, so IB is constant. Therefore when with the increase in the collector current, IE also increases, so this will increase the VE, this will in turn increases the VE. So therefore when V is increasing, when V is increasing, there is a corresponding decrease in the VBE because VB is constant. With the help of biasing circuit, we are fixing the VB constant. So when when V is increasing with the collector current, IE is increasing, and when IE is increasing, VE increases. So whenever V increases certain amount, the same amount will be decreased by VB because VB is constant, base voltage is constant, so VB is going to be decreased by the same amount, same value. So when VB is decreasing, and will have a corresponding decrease in the IB, so therefore IC gets decreases. So that increase in the collector current is compensated by decrease in the VBE. Therefore IB decreases and IC decreases. Similarly, whenever the IC decreases, suppose if IC decreases, so similarly IE also decreases. When IE decreases, VE, this will decrease the VE. Since VB is constant, VB is constant and VB is equal to VBE plus VE. So when VE decreasing with decreasing IC, IE decreases and VE decreases. So when VE decreases, there is a corresponding increase in VB. Since VB is constant, base voltage is constant, so when with the decrease in VE, there is a corresponding increase in the VBE. So therefore, when VB is increasing, IB also IB increases. This will increase the IC. So the decrease in the collector current is compensated by increasing the VBE, since base voltage is constant. So this is how the stabilization of collector current, nothing but the operating point, is achieved in the circuit. So that is the importance of VE, that is the feedback voltage, emitter voltage, which is produced across the RE. So RE used in the circuit for stabilization of the operating point, Q point, operating point. And RC is the component used. RC provides the necessary voltage gain of the amplifier, because AV is equal to voltage gain of the amplifier is equal to current gain, that is beta, into RC by RI or RC or RL. So this gain is proportional to the collector resistor. So therefore that RC is used that RC provides the necessary voltage gain in the amplifier circuit. More the value RC, more will be the gain. If RC is decreasing, so the gain also going to be decreased. So that will RC provides the necessary voltage gain in the circuit. And another important, that is the coupling capacitor C1 coupling capacitor C1. Purpose of the C1 is to couple the input, it is used to couple the input signal to the base of the transistor, to couple input signal to the base, and also it isolates the DC condition, DC voltages. And the another parameter, that is a coupling capacitor CC. it couples the amplified output to the base of or the input of next stage. See here the coupling capacitor, this coupling capacitors, couples the amplified output signal which is obtained at the resistor, amplified output signal, that is the voltage obtained at the collector resistor RC, to the base of the next stage amplifier. So this is the purpose of coupling. And also the coupling capacitor, it not only couples the amplified signal to the base of the next stage and couples the AC to the next stage, and CC, this CC also isolates the DC, isolates the DC operating condition, not to alter the biasing conditions of the next stage. So the coupling capacitor couples the amplified output signal to the next base of the input of the next stage, and also it isolates the DC biasing conditions. It isolates the DC biasing conditions of the one stage to the next stage. Therefore, it is not going to alter the operating point of the next stage. That is the purpose of a coupling capacitor. And coming to another important component in the circuit, that is the emitter bypass capacitor, CE. So CE, if CE is not there, when CE is in the absence of CE, then the voltage drop, more voltage drop takes place at the RE. So therefore the gain is going to be decreased, voltage gain. So because of this, the gain, voltage gain decreases. So to avoid the effect of negative feedback, so to provide a necessary gain, so we have this capacitor, emitter capacitor, acts as a bypass capacitor. It is a bypass capacitor, bypassing the signal, amplified signal. So therefore it's going to reduce the effect of negative feedback and bypasses the amplified AC signal, bypass capacitor. So these are the purposes, use of each component in the circuit. So coming to the operation, when we give the input signal V in to the amplifier, when we apply, this is the signal to be amplified. When we give as input, this is the input signal. When that is given, when we give the signal to the base, the coupling capacitor couples the signal to the base of the first stage amplifier. So the first stage amplifier amplifies the signal. The Q1 amplifier, that first stage RC coupled amplifier, this amplifier will amplify the signal. Q1 amplifies the signal, and amplified signal obtained at the collector of first stage. So this amplified signal is now coupled to the base of the next stage, second stage, through the coupling capacitor. Now the second stage amplifier amplifies the signal further, and finally the amplified output signal, again the second stage amplifier amplifies the amplified signal of the first stage, and the amplified signal of the two-stage RC coupled amplifier is obtained at the collector of the second stage RC coupled amplifier, and that will be connected to the load. So we have the amplified signal will obtain across the load. So we have a maximum current that is flowing through the load. So we have a large voltage drop across RL. So this is how the RC coupled amplifier is working. Two-stage RC coupled amplifier is working. Coming to the frequency response of the RC coupled amplifier. So the frequency response of amplifier is studied. We can divide that frequency range into three regions. That is low frequency region, shown in the blue. This is the low frequency region, and this is the high frequency region. This is low frequency region, and this is the mid frequency, shown in red. Mid frequency, high frequency shown in green, and low frequency shown in blue. So these are the regions. How the gain here, the frequency response of RC coupled amplifier is the curve showing the variation of the gain. Here gain is varying on the y-axis with the signal frequency, input signal frequency. See, when we see the frequency response curve, we can observe that the gain falls both at low frequency and high frequencies region, and it remains constant in the mid frequency region. So low frequency region, is around below 50 Hz, and mid frequency region 50 to 20 kilohertz, and high frequency region is the above 20 kilohertz. So this is the frequency response curve. So here, coming to the bandwidth of the amplifier, RC coupled amplifier. See here, this is the maximum gain. So when the gain falls to, when this is the gain, that gain falls to, this is the point, these are the points when the gain becomes 7.707 times of the maximum value. This is the maximum gain. So this is the point corresponds to 0.707 times of the maximum gain, Amax. So when this point corresponding to the 0.707 times of the maximum, the frequency corresponding to the gain 0.707 times of the maximum gain are called as cutoff frequency. So in the low frequency, the frequency corresponding in the low frequency region, the frequency corresponding to the 0.707 times of the maximum gain is called lower cutoff frequency. In the high frequency, the frequency corresponding to the 0.707 times of the maximum gain is called the upper cutoff frequency. And the frequency in between this difference, the range of frequencies falling in between lower cutoff and upper cutoff frequencies are known as its bandwidth. It is known as the bandwidth of the amplifier. See, so why there is a reason. Let us see why the gain decreases in the low frequency region and also in the high frequency region, and why the gain remains constant in the mid frequency region. In the low frequency region, why the gain rolls off decreases in the low frequency region, because the coupling capacitor, the reactance of the coupling capacitor is very high at low frequencies. Xc is equal to 1 by 2 pi Fc. So when frequency of the signal is very low, reactance of coupling capacitor will be very high, so that the will not allow the signal, so the gain is the input signal will not allow the signal. So very small part of the signal will pass from one stage to the next stage because of the coupling capacitor. So therefore the gain decreases at low frequency region. So the coupling capacitor and the emitter bypass capacitor offers very high reactance. Coupling capacitors and the bypass capacitor access very high reactance to the amplified signal. So a low signal, very small part of the signal passes from one stage to the next stage using coupling with the coupling capacitor for amplification. So the signal amplified is very small, and also the emitter bypass capacitor cannot shunt effectively the emitter resistance RE effectively, so that we have more drop across the RE. So that is also going to decrease the gain of the amplifier. So the reason why the gain falls at low frequencies is because of the reactance of coupling capacitor. Coupling capacitor increases with the when the frequency is very low. So this is will not when the reactance is very high, it will not allow most of the signal. So therefore a small part of the signal will flow from one stage to another stage for the amplification. So the signal more reactance to the amplified signal, so the voltage gets reduced. So therefore the gain falls because of the coupling capacitor, and also the emitter bypass capacitor is not effectively shunting the RE So therefore that also, because of it is not bypass, the amplified signal not bypassed for completely, so therefore some voltage will fall across the RA, that will acts as a negative feedback, so the gain decreases. So these are the reasons why the gain falls in the low frequency region. In the high frequencies, at high frequencies above 20 kilohertz, the reactance of coupling capacitor is very low, so the signal gets coupled effectively, but the inter-electrode capacitance, the reactance of capacitive reactance of base emitter junction, so that is the inter-electrode capacitors. Here in the high frequency region, so we have the base and emitter. In the frequency region we have a capacitor, base and emitter we have a capacitor, and base and collector we have one more capacitor. So this base acts as positive plate and emitter acts as negative plate. Similarly, base acts as positive plate and collector acts as negative plate. So these are known as electrode capacitors, will come at high frequencies. Electrodes acts as capacitor plates of the capacitor, and material acts as the dielectric, air acts as dielectric. So the electrode capacitance will come in effect of electrode capacitance, reactance of electrode capacitance is very low at high frequencies. So this will effectively short circuiting the terminals, so the signal not gets amplified properly. Instead of amplifying, the signal is directly passing from the input to the output. So that's why the gain decreases at high frequencies, because of the electrode capacitance of the transistor. And so therefore, when at high frequencies the coupling capacitor reactance is very low, so when reactance is very low, it increases the loading effect of next stage, and that reduces the voltage gain. So loading effect of the next stage will come. So when the reactance is very low, here at high frequencies, when the reactance of this coupling capacitor is very low, when Xc is very low at high frequencies, when frequency increases, Xc decreases. So when the reactance of coupling capacitor is very low, then it acts as a short circuit. So therefore, the resistance of the second stage will come in parallel with the first stage. So that will cause the base of resistance of the second stage acts as a load for the RB2, acts as a load for in the first stage. So this is called as loading effect. This loading effect will reduce the overall load resistance. RL dash gets reduces, so therefore the gain decreases, gain falls in the high frequency region because of the loading effect. So when at high frequencies the coupling reactance is very low, coupling capacitor, so that because of this there is a loading effect of the loading effect on the load resistor from the next stage, second stage to the first stage. And coming to why the gain remains constant. The gain remains constant in the mid frequency region. So we have studied two effects. The gain decreases both at low frequency and also at the high frequency region. And why here in the frequency response we have observed that the gain remains constant in the mid frequency region. So in the mid frequency region, the reactance of coupling capacitors in the mid, as the frequency increases, reactance decreases. Reactance of the coupling capacitor in the mid frequency region, the reactance of the coupling capacitor is very low, so that will increase the gain. So when the reactance is very low, when reactance is low, more the loading effect on first stage, higher loading effect of on the first stage, and hence the gain, lower gain. And when the reactance is very low and a large part of the signal is coupled, so two things simultaneously will observe across the coupling capacitor. The reactance in the mid frequency region, the reactance of the coupling capacitor is very low, so this will affect so most of the signal will be coupled from one stage to the next stage, so that will increase the gain, shown in the blue arrow. But when the reactance decreases, at the same time the loading effect of the second stage base resistance will come in parallel with the first stage collector resistor RC, so loading effect will reduce the gain. So two simultaneous things will happen because of the decrease in the reactance of the coupling capacitor. One will increase the gain because of the low reactance. Most of the signal coupled from one stage to the next stage, so that signal gets amplified further, so the gain increases, shown in the blue arrow. But with the decrease in the reactance, the loading effect will increases, and that will reduce the gain. So two things simultaneously happens, gain increases and decreases simultaneously, so the resultant gain remains constant in the mid frequency region. Advantages of RC coupled amplifier. So we have excellent frequency response, that is the gain remains uniform, that is the fairly constant in the mid frequency region, uniform bandwidth over the wide range of frequencies, that is possible with the RC coupled amplifier. Excellent frequency response, uniform gain in the mid frequency region. If it is operated in the mid frequencies, will get uniform gain, and inexpensive. It employs the resistors and capacitors which are very cheap, and it is very less in size, compact. It provides less frequency distortion. Coming to the disadvantages are low voltage and current gain, and become noisy with age and moist climates. Impedance matching is very poor. The load is not coupled effectively. The load impedance of the speaker is only few ohms, but the impedance of the circuit is very high, several hundred ohms. So we have that impedance is not proper, coupling is not proper, so signal gets lost because of the poor impedance matching. Most of the signal is amplified signal is not passing through the load, so that signal gets lost, more power loss because of the poor impedance match. Because the load impedance is very low, of the order few ohms, and whereas the load the output resistance of the load must be equal to the output resistance of the amplifier R0 must be equal to the load resistance for proper impedance matching. So then only the maximum power will transfer from the circuit output of the circuit to the load, that is R0, when R0 is equal to the RL. So this is the R0 output resistance of the amplifier, and RL is the load. So when both are equal, almost equal, the maximum power transfer when both there is a impedance matching. Because RL is very low and R0 is very high, so there is a improper matching, impedance matching, so maximum power will not transfer from the output of the amplifier to the load. So this is the drawback of a RC coupled amplifier, poor impedance matching. Applications: of RC coupled amplifier. RC coupled amplifiers have excellent audio fidelity for wide range of frequency, used as audio amplifiers in the audio frequency range. This will amplify speech and music signals, and used as voltage amplifiers in the initial stages of our public addressing system. So in this class we have discussed the working of two-stage RC coupled amplifier and frequency response of the RC coupled amplifier, factors affecting the frequency, fall of gain in the low frequency region and high frequency region, and why the gain remains constant in the mid frequency region, that is the frequency response curve, using frequency response curve, and advantages, disadvantages of RC coupled amplifier and applications. Also we have studied questions quiz. RC coupling is used for amplifying the voltage, current, power, none of the voltage amplification. In general, RC coupled amplifier voltage gain and over mid frequency range is constant. It is constant. Changes abruptly with frequency is constant. Changes uniformly with frequency, and none of those. So changes uniformly with the frequency in the mid frequency region. In the initial stage of multi-stage amplifier, we use RC coupling, transformer coupling, direct coupling. In the initial stage of multi-stage amplifier, we use RC coupled amplifier. RC coupling is not used to amplify extremely low frequencies because there is a considerable power loss, there is a hum in the output electricals, so gain is very high, considerable power loss. In the low frequency, extremely low frequencies, because there is electrical size of coupling capacity becomes very large. Questions frequently coming in the examination, frequently asked questions are: draw the frequency response of RC coupled amplifier and explain the frequency response of RC coupled amplifier. Explain the working, construction and working of RC coupled amplifier. Explain why the gain falls at high frequency as well as at low frequencies, and explain why the gain remains constant in the mid frequency. List the advantages and disadvantages of RC coupled amplifier. List the applications of RC coupled amplifier. So we'll stop here this class, RC coupled amplifier. In the next class we are going to study the two-stage transformer coupled amplifier. We are studying the multi-stage amplifiers in this second chapter. So far we have studied the classification of amplifiers, multi-stage amplifiers, need of multi-stage amplifiers, gain, bandwidth and frequency response of multi-stage amplifier, and today we have studied the RC coupled amplifier, two-stage RC coupled amplifier working, frequency response, advantages, disadvantages and applications.